Hello, my name is Rebecca Muller. In today's lesson, we're going to look at how to solve graphically and analytically equations involving roots, and then we're going to also look at some applications of root equations. Let's begin by looking at a property that's going to help us solve equations involving roots and radicals. If P and Q are algebraic expressions, then every solution of the equation P equals Q is also a solution of the equation P to the nth power equals Q to the nth power for any positive integer n. What this tells us is that we can raise both sides of an equation to any positive integer power and have equivalent solution sets for the equation that we started with. Let's look also at the steps then that might be involved in trying to solve an equation analytically. The first step that we'll use is to isolate a term involving a root on one side of the equation. Next, we'll raise both sides of the equation to a power that will eliminate the radical or rational exponent. Third, let's solve the resulting equation, repeating steps 1 and 2 as needed to eliminate the radicals. And then finally, we need to check all proposed solutions in the original equation. As our first example, we're going to consider the radical equation, which reads the square root of 3x plus 4 minus the square root of 2x minus 4 equals 2. Now, as you recall, step 1 said to isolate any radical expression. Since we have an equation that has two radical expressions on one side of the equation, our first step will be to isolate one of them. I'm going to choose to isolate the first radical expression. And the way I'll do that is to add the square root of 2x minus 4 to both sides of the equation. When we do that, we end up with the equation that looks like this. The square root of 3x plus 4 equals 2 plus the square root of 2x minus 4. Now, our second step is going to be to raise each side of the equation to an appropriate power which will get rid of the radical. And the power that we need to use is squaring, since it's a square root. So what I'll do next is to square both sides of the equation. Now, a common mistake in this step is to think that all I need to do is square each term. But instead, notice that the rule told us we could square both sides of an equation, not each term in the equation. Therefore, when we actually carry out the squaring process, we do get rid of the radical on the left, and we end up with 3x plus 4. On the right, in order to multiply out, this is in the setup of a plus b squared. So we'll end up with the first term squared plus the product of these two terms doubled, which will end up giving us 4 times the square root of 2x minus 4, plus the last term squared, which will eliminate that radical expression, that radical sign that is, and give us just plain 2x minus 4. Now we're going to repeat the process as needed. Notice we still have a radical expression in our equation. In order to do that, I'll begin by subtracting 2x from both sides of the equation. What that gives us is x plus 4 on the left-hand side. Notice also that the 4's on the right-hand side of the equation actually subtract out. So we've moved the 2x, we've subtracted it from this side of the equation, and we're left with 4 times the square root of 2x minus 4. Now, the radical term is isolated, so what we can do in the next step is to repeat the process, and that is to square both sides of the equation again. Here, we put the squaring, and evaluate. X plus 4 squared gives us x squared plus 8x plus 16. On the right-hand side of the equation, the squaring is going to give us 4 squared, which is 16, times the square root of 2x minus 4 squared, which gives us, in parentheses, 2x minus 4. Now, we need to simplify further. Notice we have no radical expressions left in our equation. I'm going to use distributive property on the right-hand side of the equation and rewrite this as 32x minus 64. Then notice what we have is a quadratic equation. And so therefore, what we're going to do is to set this equation equal to 0. In doing so, we end up with x squared, and I'm going to subtract 32x from both sides of the equation. And what that will give me is a negative 24x. And then I'll also add 64 to both sides of the equation, which ends up giving me a positive 80 equal to 0. Now, let's continue this problem on the next sheet. Again, rewriting the equation, we have x squared minus 24x plus 80 equals 0. Since this is a quadratic equation, what we would next try is to look and see if we can find factorization of that quadratic since it's set equal to 0. The factors of 80 of 4 times 20 are going to work here. If we write x minus 4 multiplied times x minus 20, notice that our middle term upon multiplication will be the negative 24, and the negative 4 times the negative 20 gives us the 80. Setting each of the factors equal to 0, x minus 4 equals 0, or x minus 20 equals 0, will give us solutions to that quadratic. Now, if you recall, the property said that we would have the same solutions for this equation. In other words, the solutions to this equation will show up as also solutions to our original radical equation. But one thing that happens is that we have restrictions on square roots. We know that we cannot take square roots of negative numbers. We also know that the square root of a number cannot equal a negative value. For that reason, because we've eliminated the radical expressions, we now need to check both of these solutions to make sure that they actually will work in the original problem. To do so, we're going to take 4 and replace x in our original equation. That would give us 3 times 4 plus 4 minus the square root of 2 times 4 minus 4. And what we're trying to discover is whether we actually get the solution of 2. Let's evaluate this. We have 3 times 4 is 12, plus 4 is 16. So the first term ends up being the square root of 16. Minus 2 times 4 is 8. 8 minus 4 is 4. So that's the square root of 4. Now, square root of 16 is 4. Minus square root of 4 is 2. And this solution does check. We also, however, need to take our second solution and check it in the equation also. Now let's check x equals 20. We're going to substitute in place of x. So we'll have 3 times 20 plus 4 under the first radical, minus the square root of 2 times 20 minus 4 under the second radical. And the question is whether this equals 2. To evaluate, 3 times 20 is 60 plus 4 gives us the square root of 64, minus, under the second radical, 2 times 20 is 40, minus 4 is 36. And we get 8 minus 6, which does equal 2. So both of the solutions that we found, both 4 and 20, check in this equation. Now let's see how we can use our graphing calculator in order to support our results. I've entered into the y equals key the equation is the square root of 3x plus 4 minus the square root of 2x minus 4, and then minus 2. So in essence, I've set the equation equal to 0. What we'd like to do next is to graph this, and I'm going to choose a window from 0 to 30 for my x value, and negative 1 to 1 for my y values. And when we look at the graph of the equation, what we'd be considering would be the x-intercepts. If we wanted to sit and look at the tick marks, we can see the first one looks like it's on 4. If we count it off, we would find the second one is also at 20. But we could also double check this by going to our intercepts. Let's calculate the 0 of the function. And I'll go ahead and do the one to the right first, the left bound, and enter, and then a point to the right, and enter, and then guess. and we get the solution of 20, 0. We could perform the same type of a check on the solution 4. Now we'd like for you to try a problem on your own. I'm going to give you a radical equation and ask you to think about the steps. Isolating the radical first, raising to a power that's appropriate, and then solving. And don't forget before you finish the problem to check your solutions. Go ahead and turn off the tape when you see the equation that is, and when we come back we'll work this together. Solve the equation, the square root of 3x plus 4 equals 8 minus x analytically, and support the result graphically. Let's see if you were able to get the correct solution. Our equation, square root of 3x plus 4 equals 8 minus x, has a radical already isolated. We're going to choose an appropriate power, which in this case would be the squaring, since this is a square root. And we will square both sides of the equation. Let's evaluate this. The square root of 3x plus 4 squared is 3x plus 4. Squaring on the right-hand side of the equation gives us 8 squared, 64, minus twice the product, which would be 16x, plus x squared. This is a quadratic equation, so in our next step, what we're going to choose to do is to set this equation equal to 0. And in doing so, I'm going to subtract 3x from both sides of the equation and 4. I'll also reorganize to put the x squared term first. So we're going to have 0 equals x squared, subtracting 3x gives us minus 19x, and subtracting 4 gives plus 60. Next, we're going to consider whether we can find factors of that quadratic. Factors of 60 that would add together to give us negative 19 are negative 4 and negative 15. So we can factor this as x minus 4 times x minus 15. Setting each of these factors equal to 0 will give us possible solutions to this radical equation. And we come up with two possible solutions, 4 and 15. Remember, these are possible solutions because we now need to check our work. Let's take the first of our possible solutions, x equals 4, and substitute this into the equation, the original radical equation. We'll have the square root of 3 times 4 plus 4. And the question is whether that equals 8 minus 4. Underneath the radical, we get 3 times 4 is 12, plus 4 is 16. On the right-hand side, 8 minus 4 is 4. Now, the square root of 16 does equal 4, so our solution of 4 is correct. Let's try the second possible solution of 15 and perform the same operations. We'll have the square root of 3 times 15 plus 4. And we want to see whether that's going to equal 8 minus 15. Under the radical, 3 times 15 is 45, plus 4 is 49. 8 minus 15 is negative 7. Now the square root of 49 we know is equal to the principal square root of 7, and that is not equivalent to negative 7. 15 is called an extraneous root. We do not include it in the solution set. We would say that the solution to this equation is simply the value 4. Now, in addition to looking at radical equations or root equations, we can also look at what happens when we look at inequalities. In order to get the rule for what we're going to do with solving inequalities involving roots, let's look at that next. The solution set of f of x greater than 0 consists of all x values for which the graph of f is above the x-axis. The solution set of f of x less than 0 consists of all x values for which the graph of f is below the x-axis. In other words, if we look at the graph of a function set equal to 0, we can determine where the function is positive and where it is negative by considering how it lies on the plane. In our next example, we want to use an analytic method to solve the equation 2x minus 1 to the 2/3 power equals x to the 1/3 power. Then we're going to use a graph along with our results from solving the equation to solve the inequality. 2x minus 1 to the 2/3 is greater than x to the 1/3. Let's begin by solving the equation. We have 2x minus 1 to the 2/3 power, and we have that equal to x to the 1/3 power. Now, when we're trying to find an appropriate power to raise this to, notice that the index of our root is actually 3. Remember that when you have an exponent, a rational exponent, which has a denominator of 3, that really means cube roots. So what we're going to do is raise both sides of this equation to the 3rd power. What we end up getting will be 2x minus 1 squared on the left equals x on the right. Now we're going to go ahead and square 2x minus 1. This will give us 4x squared minus 4x plus 1 equals x. We have a quadratic now. Setting that equal to 0 will give us 4x squared minus 5x plus 1 equals 0. And factoring, we have 4x times x to give us 4x squared, 1 times 1 to give us the 1 at the end. And if we put negatives in both places, we end up with our negative 5x as our middle term. Setting each factor equal to 0 gives us possible solutions of 1/4 and 1. As in our other radical equations, what we want to do next is to check our work in the original equation. Let's look first at x equals 1/4. And we are substituting that into the equation 2 times x, which will be 1/4, minus 1 raised to the 2/3 power. And we want to see whether that's going to equal 1/4 raised to the 1/3 power. Let's evaluate. 2 times 1/4 is 2/4, which is 1/2. 1/2 minus 1 is going to equal negative 1/2. And notice that we have a squaring on the left-hand side that we can form now. So negative 1/2 squared will give us 1/4. We still have the cube root, the 1/3 power, but notice we don't actually have to go through the evaluation of this. We can see actually that this does check in this step. The other possible solution that we came up with was 1. Let's check that next. We have 2 times 1 minus 1 to the 2/3 power. And we want to see whether that equals 1 to the 1/3 power. 2 times 1 is 2. 2 minus 1 is 1. 1 to the 2/3. Is that equivalent to 1 to the 1/3? Well, 1 to any power is going to equal 1. We could also think of it as squaring the 1, which gives us 1, and then taking the cube root. And the cube root of 1 is also 1. So both of these solutions actually check in our equation. Next, let's consider the same equation on the graphing calculator in order to see what the solutions would be to the inequality. Under our y equals key, I'm going to clear out the equation that we had previously. We're going to put as y1 2x minus 1 raised to the 2/3 power. And notice we have to put that 2/3 power in parentheses. On y sub 2, we're going to put in x raised to the 1/3 power. Again, the exponent in parentheses. And in y sub 3, we're going to put in y sub 1 minus y sub 2. Now, I'm going to turn off the graphs of y sub 1 and y sub 2 so that when we look at this graph in a window of negative 2 to 2 by negative 2 to 2, we end up being able to evaluate what will give us the zeros of this function. Notice that with the radical equation, we can end up getting short points in the graph, whereas with polynomials, we're not accustomed to that. Now, we end up having 2 x-intercepts. These correspond to the zeros of the function which we just found, 1/4 and 1. We were asked to find out when is this y1 greater than y sub 2. Well, in order for y1 to be greater than y sub 2, what we need to have is y sub 1 minus y sub 2, our y sub 3 function, greater than 0. So back to the graph, what we need to look at is where this function ends up being greater than 0. Let's look at that now. Notice that the function is going to be above the x-axis, that is, in this section, which is going to be from negative infinity until we come down to the first zero intercept, the x-intercept, that is, which was 1/4, and then from the other x-intercept 1 on to infinity. And that ends up giving us the values that we end up having, the intervals, that is, that tell us where the function is greater than 0. Next, let's look at an application of using these root equations. We're going to have a problem where we're concerned about a hunter returning to his cabin. A hunter is at a point on a riverbank. He wants to get to his cabin located 3 miles north and 8 miles west. He can travel 5 miles per hour on the river, but only 2 miles per hour on this very rocky land. How far upriver should he go in order to reach the cabin in a minimum amount of time? Now, although it is true that probably a hunter is not going to spend time calculating how far he should go upriver, problems of this type, where we're trying to find out the minimum amount of distance between 2 points, are going to be applications that would be important in other instances. Here we have a drawing of the situation. We have the hunter. We're told that he's 8 miles to the west of a certain point. 3 miles north gets him to his cabin. He's going to walk partway along the riverbank, and he can walk faster here. And then he's going to walk along some rocky ground in order to get to his cabin the rest of the way. Now, what we want to do is to minimize the time that it takes him in order to accomplish this. In order to do that, what we're going to do is remember that time is equal to distance divided by rate. So let's begin by finding the time that it's going to take him on the riverbank. Well, his distance is given as 8 minus x. The rate, we were told in the problem, was 5 miles per hour. The time it takes him on the rocky area is going to be the distance, which is going to be this k value, divided by his rate, which we know is going to end up equaling 2. Now, I don't really want a separate variable here, so let's look at what we could do in order to evaluate k. Notice that what we have is a right triangle, and you may recall the Pythagorean Theorem, which states that the sum of the squares of the lengths of the sides of a right triangle equals the square of the hypotenuse. So we have here 3 squared plus x squared equals k squared. And to solve for k, we can take the square root of both sides of the equation and end up getting the square root of 9 plus x squared. There's the radical that we need to work with. So our distance is the square root of 9 plus x squared divided by his rate on the rocky land, which is 2 miles per hour. Now, we want to minimize that time, the total time. So what we're going to do is actually to add those 2 times together. We're going to have his total time equal to 8 minus x divided by 5 plus the square root of 9 plus x squared divided by 2. And now we're going to use our calculators in order to investigate the minimum value for this function. Let's graph the function in our standard window. So we're going to insert 8 minus x divided by 5 plus, in parentheses, the square root of 9 plus x squared, we need to close the parentheses twice here, divided by 2. Let's zoom 6. And what we note is that we do end up with a minimum value approximately here. Let's use calculate the minimum value in this problem. That's a good lower bound. Looks like I could choose probably 4 would be fine as a right bound. And we'll end up making a guess around here. And we'll end up with a value of 1.31 approximately for our minimum value x. Now, what that relates to is the fact that the distance that he should travel on the riverbank, let's go back to this graphic, is 8 minus x. And so we're going to evaluate 8 minus 1.3 to get an approximate value of 6.7 miles that he should walk along the riverbank before turning toward his cabin. In conclusion, let's remember that root equations and inequalities require a series of steps and checks to be sure of their solutions. You need to have a lot of diligence and practice in order to become proficient at these types of equations. You can also find some application problems in the exercises at the end of your section in your text. Try some now.